this talk is about deep learning for computer vision, and we will also talk about applications to Ghana context. As Dennis said, my name is Yash Bhalgat, and I am a PhD student right now at the Visual Geometry Group in Oxford. I'm advised by Andrew Gisselman, Andrea Vidaldi, and two more advisors, Joao and Iro. Previously, before I joined Oxford, I have worked as a senior researcher in Qualcomm AI research on efficient deep learning, and I have also worked in other places in the past. And yeah, let's get started. So before I even begin the talk, what is computer vision? Can someone from the audience tell me what they think is computer vision?
Anyone? Computer vision? I didn't hear that. Someone said something.
Yeah.
Please, can you? Okay. Yeah. So someone is saying using the computer to see.
Okay, using computers to see. That's yeah, that's one way to look at it. Do you have any other definitions for computer vision? Like, okay, so if computers see, what are they really doing when they see something?
So what does it mean for? So they are saying processing images.
Okay, okay. Well, actually, that's correct. So basically, you want machines to have the ability to see. And when you say see, you mean you want to understand what you're seeing. You want to process what you're seeing, right? So there's a very beautiful definition, which is discovering from images what is in the world and where it is. So basically, given a single image, you want to understand what is the image telling you, right? And you also want to understand, what it, where is the image, what are the objects in the image, and etc. So you want to really get the underlying reality of the world from images, just like human beings do, right? Now, if I show this picture and I ask you as a human being, you might understand that okay, this is a picture of someone playing football. I see the name here, which is Ronaldo, and I see the jersey, which is white and golden. So it's probably Real Madrid. So any football fans here know which game this is?
Yeah.
Yeah. Sorry, I can't hear Daniel. Can you repeat the answer that someone said?
Yeah, so they are football fans here.
Okay, okay, great. So basically, if I show this image to any of you, you can tell me what's happening, right? Now, the goal is to develop an AI which can do the same thing. Now, I gave this same image to GPT-4, and this is what it told me. I asked GPT-4, what is happening in this image? And GPT-4 told me it shows a soccer or football match. The player is wearing a white jersey with the name Ronaldo and number 7. They're performing an overhead kick. It also has a stadium with crowd of spectators, and the player is Cristiano Ronaldo. Right? So GPT-4 actually did quite well. It understood lots of things.
Yeah.
Does this mean computer vision is solved? Like, it's done. We don't need to do any research now. We should all retire.
Yeah.
All right. So, yeah, go ahead.
Yeah, so it's asking if we should close and go home because they finished it.
Yeah, exactly. I mean, so GPT-4 and other large models these days are doing really well, right? They can understand things. They can tell us what's happening. They can answer questions and things like that. But I argue that computer vision is still not solved. It's not just about telling what's happening, because this can be done by using lots and lots of data, right? That's how these large models have been trained. But the question is, do they actually understand the world? And the answer is probably not. So you can see lots of examples on Twitter, on other websites that show many examples where you ask simple. Sorry, I can't hear what they are saying.
You can continue. Yeah.
Okay, so you can see lots of examples out there which show that if you ask very simple questions to these large language models, they can't actually answer them. So I don't think they really understand the world. So then the question is, how do we make them understand the world, right? So this is the holy grail of computer vision, and the research right now in both academia and industry is going towards this direction. Right now, it's a very huge area of research, and we only have 30 minutes. So I'm not going to go into many details, but I'm just going to give you a very quick overview of different problems in computer vision and the current progress in research that has been done to solve these problems. Okay. So, and let's make this session a bit interactive. So, if you have any questions, please interrupt me, Daniel. You can ask me any questions if you want, if you have from that side. But let's also keep in mind we only have 30 minutes. So let's move on. Okay, so I know all of you are students here in the audience. So if you really want to understand computer vision and if you want to get a very good understanding of this field, I would highly recommend these two books. And the second book, Multiple View Geometry in Computer Vision, is from my PhD advisor, as you can see, Andrew Gisselman, and it's considered the Bible for multi-view geometry, which is 3D geometry. And the other book is Foundations of Computer Vision by Antonin Torralba, Philip Isola, and William Freeman. This book actually came out just this year, and it's very, very recent. So it has all the recent progress in computer vision, and it's an excellent book. So anyone who is interested in computer vision, I suggest that you read these books to understand, the history of computer vision and also the current progress in computer vision. All right. So how has computer vision, been throughout the history? In the very old days, before 1990s, it mostly consisted of geometric vision. So you wanted to understand how images are formed, like how do if you have multiple images, can you reconstruct the scene from that? So that's called multi-view geometry. Can you estimate the shape of objects just from the shading of the objects? Or there was a very popular idea called blocks world, which was to represent the real world in terms of very basic primitives called blocks. So instead of modeling the world as a very complex world, you would decompose the world into basic blocks and use those blocks to understand the world. You can understand motion, you can understand physics, mechanics, everything using blocks world. That was the idea back then, before 1990s. Now, between 1990s and 2000s, cameras became very popular, right? So people could actually capture lots of images. So researchers began to wonder, how does a human vision work? And they tried to use the human vision to develop algorithms for computer vision. So lots of research happened for image segmentation. There were many algorithms which performed face detection, object detection, and the learning based methods were just getting started. So before this time, the focus was mostly on non learning methods. And within this decade, people began to start thinking about, can you learn things based on data? But it was not yet still there. And then between 2000 and 2010, the focus again. Sorry. Daniel, you have to repeat
Yeah,
the question
yeah.
again.
So, yes, continue. I think there's a problem. Sometimes some people join with their audio on. Yeah.
Okay. So between 2000 2010, the focus again shifted to a bit more of geometry based vision. So there were lots of key point descriptors. You might have known of SIFT and SURF and all these different detection descriptors in computer vision. They were used for tracking objects in 3D. There was a popular topic called SLAM. So SLAM basically stands for simultaneous localization and mapping, which is very important for robotics and autonomous driving. And there were a few small scale data sets that came in this decade. For example, there's a very popular data set called CIFAR, CIFAR, which was released between this decade. Now, people mostly relied on kernel-based methods during this time and very traditional ML methods like SVMs or linear regression for computer vision. Now, after 2010, this was the birth of deep learning, basically. And this happened because you had lots and lots of data available. There was a popular benchmark called ImageNet, which consisted of million images, which were properly curated, and it was now possible to train these deep networks using this data. So this was the time when we really began to think about deep neural networks, and we slowly actually reached beyond human level understanding. And now, as you know, in the last few years, the research has focused on large scale methods. So we have LLMs, we have VLMs, multimodal models, lots of large models. So that has been the focus for the last few years now. Okay, so this is how the progress in computer vision has progressed throughout the history, and we are going to focus this talk on the deep learning part of computer vision only. Okay, so what are the different problems in computer vision? You can perform image classification, which basically means what is the dominant object in the image. So as you can see on the left hand side of the slide, given this image, a model predicts that the image likely consists of a mite, but maybe it's also a cockroach, maybe it's a tick, maybe it's a starfish, right? So as you can see, there is a decreasing probability for different predictions. So the most probable prediction is mite, and other predictions have a lower probability. Similarly, for this image, the model says that it is most likely a container ship, but it could also be a lifeboat, it could be amphibian, it could be a fireboat, etc. So this problem is called image classification. Given an image, you are supposed to tell what the image consists of. So it's a very basic task. I think it's been solved mostly now with the modern methods. But if you go beyond just telling what's in the image, there is a task of object detection, which means tell me what is in the image and where it is exactly in the image. Okay. So on the right hand
Hello,
side of the slide,
can you hear me?
yeah, Daniel, yeah.
Yeah, when you were, is this, can you move to the previous slide? I think we lost you for some few seconds.
Okay. So which part?
Okay, yeah, okay. So this was what we were. Yeah, I think you were here. When you were transitioning, that's where we lost a bit.
I was just saying
Okay, the
that
next
in
slide.
this slide, yeah. So the
Yeah,
point
so you
is that
can move
in
to the
this,
next slide.
yeah. So in this talk, we are going to focus on deep learning, and that's it. All right.
Yeah.
So on the right hand side, you can see an example of object detection, which basically is that you have an image, a very complex image, and you want to tell what are the objects in this image and where exactly are they within this image. So you want to also localize the location of the object. So as you can see, there's a person, there's a bicycle, there's a car, there's a truck, there's a traffic light here, right? And you are supposed to predict where the objects are also within the image. So that is a task of object detection. Then there's a task of image segmentation. So in this case, it's the same thing. You also need to predict where the objects are, but it's a bit more fine grained because previously it was okay to just predict a bounding box for the object, but now you are also supposed to predict a mask for the objects. All right. Now, if you go beyond just a single image, if you think of a video, right, where objects are moving here and there, you can estimate something called optical flow. So optical flow means which pixel in image number one corresponds to the pixels in image number two. Okay. So this is a very important problem within the context of video understanding, and it helps us solve a lot of problems such as object tracking and also 3D reconstruction. And there's one more task called depth estimation. So depth estimation basically says what is the depth of every pixel in the image. So if you are given just one image, usually it is impossible to say what is the depth of the image, like in principle. But as a human being, if you're just shown one image, you can probably say, which object is far away, which object is close by, and so on. And you can do it because you have seen lots of other similar images. So you have seen lots of data. That's why, given any image, you can probably tell me what is the depth of the objects within the image. And that's the same thing with deep learning. That if you train a deep network on enough data of depths, that deep network can predict the depth for any new image. All right. So is everyone following so far?
Yes, I think they are following. Yeah.
Okay. All right. So let's move on to the architectures, right? So what exactly do we use to solve these problems? I think Avoka talked about, gave an introduction to deep learning, which told you how different deep learning models are trained using backpropagation. But now the question is, how do you design these models to solve specific problems in computer vision? So in the very beginning of computer vision, there was something called convolutional neural networks. Now I'm not going to go into many details of this approach, but the idea is that you can train very efficient models using the convolution operation. And the convolution operation basically says that you take a certain kernel. So kernel is just an array of size n cross n, and n can be very small. So you take a certain kernel of learnable parameters and you slide this kernel over the image and compute the output for every pixel in the image. So if you have this image of a dog, you can take a very small kernel like this, and you can place the kernel over different parts of the image and compute a value for every pixel in the image. And you get some output, and you can compute this with different kernels within a layer, which can give you a very high dimensional output for a certain image. And do this for multiple layers of the network. So the term deep network means that you don't just have one layer, but you have maybe hundreds of layers of convolutions and activations. And you do this and you train this network using some ground truth data. So the data can be given this image, I know it's a dog. Given some other image, I know it's a cat. Given some other image, it's a fish. So if you have these pairs of images and the corresponding labels, you can use that data to train this convolution neural network. And it was shown in 2011 that there was a network called AlexNet, which outperformed all the existing approaches in machine learning until that point. So basically, people were using SVMs and kernel-based methods, which were non-deep learning methods before 2011. But in 2011, an author, proposed AlexNet, which basically outperformed all the previous methods with a very huge margin. And this was the birth of deep learning, basically. This was the very first approach that kind of convinced people that deep learning can be actually a very useful tool to solve problems. And after this network, a lot of other innovations were done, such as there was a network called VGG16. So as you can note, the VGG basically is the name of my current lab where I'm doing my PhD. And this network was proposed from one of the authors from my lab, and it won the ImageNet competition in 2012, and it is very popular even today and has been used to extract very useful features for different images. There are many other innovations, such as there's a very major paper from 2015 called residual networks. And the idea in this paper is that you can make deep networks very, very deep. So basically, for example, VGG16 only had 16 layers, or AlexNet only had 11 layers. But the residual networks could have 1,000 layers. And the way they could achieve this is by using something called a skip connection. So basically, what they do is they take the input and they add the input to the output of a certain layer after some point. So as you can see, these connections are basically the skip connections. And when you do this, it solves many problems with the backpropagation algorithm. Specifically, there's a problem called vanishing gradient, which is that if you have many layers within a deep network, the gradients that get propagated from the last layer to the first layer can vanish, can become very, very small and can kind of, harm the learning of the model. So it can be very detrimental to the performance of the model if you increase the number of layers. But if you add these skip connections, then the gradients can actually propagate through these skip connections. And this avoids the problem of vanishing gradients and can lead to much better and much larger deep networks. This is one of the major innovations that led to the birth of very, very deep networks. And after this, there have been hundreds of papers in this area which proposed even better approaches to deep learning. But These are the building blocks of convolutional neural networks. So I'm going to move on to transformers, but before I do that, any questions about CNNs?
Any questions about convolutional neural networks? Okay, so we can move on to the transformers, I guess.
All right. Okay. So, as you might have heard, transformers now are very popular for computer vision, and not just computer vision, they're also popular for almost every area in deep learning. So they were first proposed in the paper called Attention is All You Need in 2017, and they were proposed mainly for natural language understanding. So they were mostly applied for text understanding tasks for a few years. But then in 2020, there was a paper called An Image is Worth 16 cross 16 Words. And this was one of the first papers which used transformers for large scale computer vision understanding. Okay, so the approach they had was called a vision transformer, and the basic idea was that you take an image and you break it down into multiple patches. So you can break it down into 3 cross 3, 9 patches, or you can break it down into 16 cross 16, so 256 patches. It depends. But you break it down into multiple patches and you pass these patches to a transformer models just like you would pass it to any text-based transformer model, right? So basically, you have these patches, you assign a positional embedding to each patch, so you know what is the position of the patch in the image, and you project them using a simple linear projection layer. So you have these the embedding for each patch and the corresponding positional embedding too, and this goes into the transformer which predicts the class of the image. So it can be used to predict the image label. It can also be used to predict image segmentation, object detection. Lots of other approaches have been proposed after this point. So the main takeaway here is that the architecture for the transformer architecture is very similar for both vision and language. Okay, and this is very important because what happens now is that you can combine both vision understanding and language understanding into the same model because of the transformer architecture. So the self attention and the cross attention mechanisms that transformers have enable lots of multimodal applications where you can combine information from both image and text together. But the problem with transformers is that the self-attention mechanism that transformers use is actually quadratic. Convolutions actually are linear, so it's much more efficient to compute, and also they're very friendly with the hardware accelerators that people use. But attention actually is quadratic, so it can lead to very high memory usage and also very slow inference. So we are kind of restricted to use less number of patches to avoid having lots of memory consumption. That's one problem. The second problem is that vision transformers lack the inductive bias that CNNs have. For example, CNNs have a bias of locality, so you only use the kernel to look at the pixels just around the current pixel. But in transformer, you're looking at the entire image at once, which could be a good thing, but also it's also a bad thing because now you need a lot of data to train these transformers. Now let's look very quickly at what the self-attention model looks like. So basically you have this input tokens, which is just the patches that we had right now. So you can take the image, break it down into patches. So you have these input tokens as the patches, and or it can just be the output of any of the transformer layers, right? So let's say you have n tokens. Now the way you perform the self-attention is that you map this array of tokens into a query array, a key array, and a value array. So Q is query, K is key, and V is value. And you compute an attention map using the query and the key vectors. So if you have, let's say, 100 query vectors and 100 key vectors, you will get a 100 cross 100 attention map. And you use this attention map and multiply it with the value vector to get the final output. Okay, so basically what you're doing is you're using the query vectors to compute how much any of the key vectors matter to the final output, and then you're using these weights that you compute, the attention weights, to you know, decide how much weight you want to give to every value vector and compute the average as the output. Is this clear? Because this is very important to understand how transformers work.
Please, any questions with regards to this? Okay, we can continue.
Okay.
I guess they
Um,
understood it. Yeah.
yeah, I have been very good at explaining stuff, I guess.
Yeah.
All right. Okay, so this is how vision transformers work. I have given a very high level introduction. You can go and read papers and understand better about this. But let's now talk about how they're actually used, right? So as I said before, vision transformer require a lot of data to train. But that's a bad thing and that's a good thing also, because people have observed that if you have a lot of data to train these models, then vision transformers actually perform really well. Like they can outperform the convolution networks by a huge margin in lots of tasks and give you many interesting emergent properties. For example, this is a paper called Dino from Meta, which came out a few years back, and they trained a transformer model using self-supervised learning. Now, self-supervised learning is something where you don't have labels for the data, but you can still learn very interesting features from that data. So as you can see, the moving thing above is an output from Dino, and what we are seeing is that uh, the outputs are basically the features that are computed using this image, this video. And what's interesting is, even though this puppy is running in the video, the pixels of the puppy, right? So the you can see the head of the puppy is always green, and the legs of the puppy are always red, and the body of the puppy is always blue. So it's very interesting because the model now understands that this part of the image is always the head of the puppy, and it can kind of always track the pixels throughout the video. So this is very interesting, and it's quite difficult to attain using traditional deep learning methods. And Dino can do it quite effectively. And there is one more upgrade called Dino version 2, which came out just last year, and it's even better. As you can see, the outputs are much smoother, much more consistent, and it's just amazing. So I think vision transformers can do many cool things if you have enough data to train them. And as OpenAI or Google or Meta has proven, uh, you can actually get lots of data from the internet. So data is not the problem. The problem is how you train the models with this data, right? So that's why vision transformers are actually a really popular approach nowadays for most problems. One more example is something called segment anything. So you might have seen this model that came out from Meta last year, and this has been one of the most impressive, models out there, and very popularly used nowadays. Basically, as I said, segmentation is the task where you want to output masks for the objects in the image, and in this case, segment anything can basically segment anything. So you give it any image, and it will give the segments for all the objects in the image. It does not matter what the objects are, it just works for any object. It won't tell you what the object is. So basically, it outputs the masks without telling you the label of the objects. But still, the masks are very useful for many downstream applications. So this is one more example of a transformer model which can very effectively solve a very important problem in computer vision called image segmentation. All right. So I think we have maybe 10 more minutes. Is it right, Dennis?
Yeah. Yeah.
Okay. So let me quickly talk about a very important and very popular thing in computer vision called generative models. As you know, this is the current hype. Everyone wants to work on generative models. Uh, so exactly, I'm not going to go into the details of how these models work, but I'm going to give you a quick overview of what's happening in this field. Okay, so what we discussed until now were something we call discriminative problems. So discriminative means given an input, you want to predict something about it. So you want to give me the class label of the input, you want to tell me the segmentation of the inputs, etc. So these are all discriminative problems. Now the opposite of that is generative problems. So basically, if I gave you an image of a dog, and I ask you, what is this image? You tell me it's a dog. So that's a discriminative problem, right? But if I tell you, just generate an image that looks like a dog, that's the complete opposite of what we talked about before. So it's called generative models. And previously, there have been lots of interesting approaches to this. A very popular approach for generative modeling was something called GANs. You must have heard about this. It was very popular for almost 10 years, and now no one cares about GANs almost. So it's called generative adversarial networks. And the idea here was you have something called a generator and you have something called a discriminator. So discriminator is something which, as I said, tells you what the image is, and a generator is something that generates an image that looks like what you want, you know. And they play a game basically. So the generator tries to fool the discriminator, and the discriminator tries to catch the generator. And if this game is played properly, the model can generate really interesting outputs. Now, this was quite popular for the last decade, and many outstanding approaches have been developed in GANs. But recently, in 2021, there was a paper which basically showed that something called diffusion models can outperform these GAN models. So the paper was called Denoising Diffusion Models, Probabilistic Models, DDPM, and it basically showed that there is something called a diffusion process, which is start from pure noise, and from that pure noise, you can very effectively generate high quality images of what you want. For example, these are the outputs from a model called DALI from OpenAI. And let's say I ask the model, create an image of a Shiba Inu that looks like a loaf of bread. It can do it quite well, right? It's a very cute image of a dog which looks like a loaf of bread. It's completely ridiculous because this image does not exist in the real world, but the model can still create this image just as if it's very creative in doing these things. Another example is I asked the model to create a Da Vinci design of a futuristic self-driving vehicle. Now, Da Vinci existed in 1700s or 1800s, and obviously he had no idea what self-driving vehicles look like. But the model can still kind of hallucinate what would Da Vinci draw if he wanted to design self-driving vehicles, and this is what it gave me. So it's a very creative process, and obviously it's not completely magical because these models have been trained on lots and lots of data. There's a certain component where the data has something to do with the quality of the outputs, but beyond data, there's also something really interesting about diffusion that makes it work so well. So I would highly recommend all of you to read a bit more about this. There's a many interesting models out there called latent diffusion, called stable diffusion, as you might have heard, is a type of a latent diffusion model. There's something called a DDIM. There's many other models which you can look at. Okay. Now there's also, if you go one step further, you also want to generate videos, which is much difficult than generating images, because in a video you want the different frames to be consistent, right? They can't be just any frames. They have to be, there should be a very strong relationship between different frames of the video. For example, it should be 3D aware. It should be correct. The characters in the image should be consistent. For example, you have this mouse painting something, right? So across the entire video, the mouse should look the same. The the face of the mouse cannot change, right? So achieving this is quite difficult, and people have made lots of progress in the past 2 years on this problem. There's many models like Sora from OpenAI. There's Dream Machine from Numa. There's stable video diffusion. Many interesting models out there that you can have a look at. Okay. Now, one more thing, a very important thing is that you want to be able to have a bit more fine-grained control over what you generate. Okay, so this is called controllable generation. For example, you want to not just generate any image of certain objects, but you want to generate an image in a certain layout, right? So you can provide the model of a very rough sketch of what you want and ask it to generate something. So if you give this sketch here, it can generate the image that very closely corresponds to that sketch. Or you can provide a depth image of the model and ask the model to generate something. So this depth image generates the image of Abraham Lincoln, and there are different, there is slight variability in the images that it generates, but they all correspond to the same depth image. Okay, so this is called controllable generation. You can have a look at a paper called Control Net, which is quite popular, but there's also many other papers which solve this problem. Okay, so let's move on to the last part of the talk today, which is real world applications. Now you have all these interesting models and very powerful, algorithms that can solve lots of problems. But what are some considerations that you need to take care of when you actually use these models in the real world? Okay, excuse me. So one of the main problems is that these models can be very huge and they might not be able to run on small devices. Let's say you have a smartphone and you want to run a deep learning model on your smartphone. Now, if this model was extremely huge and extremely, inefficient, then it might consume a lot of power from a smartphone, and your smartphone might just discharge very quickly, right? Or it might heat up a lot. Now, these are very undesirable things if you are a consumer that is using a smartphone, right? So, what you really want is you want these models to be memory efficient. What this means is that you want these models to use as less memory as possible, and you want them to be power efficient. So they should not drain your device completely when you're using it, right? One more thing is they should be robust to different conditions. For example, day or night changes or weather changes. So if you're using something for autonomous driving, the models should not be, they should work in every condition that the car can encounter in the real world. It should also be able to deal with unseen objects, right? Lastly, they should be safe. Basically, no one should be able to hack it, or they should not, give you unpredictable outputs in certain situations, which can be very unsafe. So you need to make sure that these models are actually safe and that you can guarantee it before you can deploy them in the real world. And what are some examples? So I think sorry, Dennis, you're saying something?
No.
Okay, so I'm going to talk about a couple of examples which are, relevant to Ghana, for example, or maybe India. So I think agriculture is a very popular source of income for citizens in our countries, and there are many problems that farmers face in their day-to-day lives. For example, plants can get infected by different pests, and they can destroy the livestock, right? So what if you can use AI to detect these diseases and kind of tell the farmers what's happening in their fields? So you can use, computer vision models. You can train them to perform classification. For example, these plants are infected with a disease called esca. So a model can predict that these plants actually have that disease just from some camera that is planted in the field. They can also tell you which leaves exactly have this problem. Uh, it can be much more accurate if you just output a segmentation map and so on. So there's a lot of work happening on pest control or disease control in plants and agricultural environments using computer vision. One more thing in agriculture is that you can use satellites to survey land to determine which land is suitable for agriculture and which land is not suitable for agriculture. For example, some lands might have a very acidic content in the soil, and that might not be suitable for agriculture, or some land might be very fertile. And you can somehow predict all of this just by using satellite images, which is very useful because if you have large areas of which have been unexplored, you can explore them just from using satellites. So that's one more application of using computer vision in agriculture. Beyond agriculture, you can also use computer vision to save your environment. There's a lot of illegal activities that happen where people destroy natural habitats to perform mining, for example, and which is quite harmful to our environment. And you can use computer vision or satellite images to identify if that's happening in some areas. Okay. One more example is healthcare. This is quite popular, and lots of applications have been deployed in the real world today. So many radiologists use computer vision to identify diseases in CT scans or X-rays or ultrasound images. For example, at the right hand side, I'm showing you an ultrasound of a heart, and this image might be, for a common man like me, it's very hard to say what this image means. You need expert doctors to really identify what's wrong in this image. But there can be, problems. There can be difficulty to access such doctors in, for example, rural areas in some countries. And you can use AI to at least solve that problem to some extent. For example, you can train some models to detect a particular kind of cardiac disease just from the cardiac ultrasound. You can detect tumors in the brain using computer vision. You can also detect fractures or some bone related issues using x-rays and so on. So many important medical applications can be enabled using computer vision. Okay. And lastly, I think we have to stop the talk now, but we haven't covered a few things today. For example, as Dennis said, I work in 3D computer vision during in my PhD, and 3D computer vision is currently I would say it's a very important topic because there's a lot of problems in 3D computer vision which have not been solved. So if any of you are considering doing a PhD in computer vision like Dennis is doing right now in NYU, I would recommend this area as a very interesting area of research. So there's a lot of problems here. There's reconstruction, segmentation, generative models in 3D. There's also vision plus language, where you combine text with vision. For example, you can ask questions like we did for GPT-4. You can use open vocabulary segmentation detection. There's also video understanding, and video understanding is also quite difficult because videos can be very long, they can be very hard to ingest, and so on. So there's a lot of problems in there, such as object tracking, point tracking, and activity recognition. So that's all for the talk, and I can take any questions if there is something you want to
Yeah.
ask me.
Thanks, Yas, so much for the excellent presentation.